The next problem is to find the Fourier transform of x of t, where x of t is given as this rectangular pulse which goes from negative t to t, and we know from the direct transform x of j omega is equal to negative infinity to infinity x of t e to the power minus j omega t dt. Okay, moving forward, x of t is equal to 1, and since this extends from negative t to t, outside of this negative t and t, the value is essentially 0. Hence, we can change the integral limit from negative infinity to infinity to the new limit, that is negative t to t. T to t, the value of x of t becomes 1 e to the power minus j omega t dt. Now, solving the integral, we get e to the power minus j omega t over negative of j omega, the limit being minus t to t. So 1 over j omega, that is negative 1 over j omega. Now plugging in the limits, the first expression becomes e to the power minus j omega capital of t minus e to the power j omega capital T. So x of j omega can be written as taking 2 on the numerator and j omega, we write only omega. The numerator, since this negative is multiplied over here, we can write it as e to the power j omega capital of T minus e to the power minus j omega capital of T. Since we have multiplied the numerator by 2, we have to divide it by 2, and there was a j over here. We take the j and multiply it with the denominator. Now, if you are familiar with the Euler expression, this is equal to twice omega sine of omega t. This can be written as two times capital T sine of pi times omega t over pi. This 2 pi cancels out and this term remains as it is. And there was a omega over here. We can write omega times t. This t and this t will cancel out and the expression remains as before. Multiply this with pi and divide it with pi. So this form is quite familiar to us and can be written as twice t sinc of omega t by pi. So this is the required Fourier transform, which is must be cared for, because if a pulse is rectangular in the time domain, it will be a sinc pulse in the frequency domain, and the converse is also true. That means if in the time domain we are given a sinc function, the frequency domain representation will be a rectangular function. So how does this plot looks like? Let us see. This will look like something like this, which is x of j omega. This value is twice t this is pi by t, this is twice pi by t, and similarly this is negative pi by t, this is negative twice pi by t. So the required Fourier transform is x of j omega is 2t sinc of omega t over pi. Hope the problem is clear to you. Now moving on to the next problem, where we are to example 9 to find the Fourier transform x of t, which is equal to e to the power minus 3t u of t. Now we know from the previous problem that we have solved the Fourier transform of e to the power minus at u of t is equal to a plus j omega inverse. So the Fourier transform of e to the power minus 3t u of t will also be equal to 3 plus j omega inverse. I'm sorry, there is a change in the question. This will be u of t minus 1. Now, from the Timeshift property, we get that x of t minus t naught will have a Fourier transform pair of e to the power minus j omega t naught x of j omega. So the given expression x of t, that is e to the power minus 3t u of t minus 1, can be written as e to the power minus 3 times e to the power minus 3 t minus 1. This is done because if we multiply this two terms, we are left with this term. This becomes minus 3t and this becomes e to the power 3, and e to the power 3 times e to the power minus 3 is equal to 1. So multiplying these two terms, we get this one, and the remain is e to the power minus t minus 1. Say this equals to z of t. So from the property, z of j omega equals to e to the power minus 3, the constant term remains as it is, e to the power minus j omega for this expression, since the shifting is t minus 1, so the value of t naught in this case is 1, and this term becomes e to the power minus j omega. And x of j omega, as we have found out, to be 3 plus j omega inverse 1. So 3 plus j omega inverse 1. So this is our required Fourier transform. Now, moving on to the next problem. Which is the example number is 10. Sorry, we are to find Fourier transform of x of t, where x of t is cos of omega naught t. Now, in the solution, given x of t is equal to cosine of omega t, which can be expanded from the Euler's expression to be half of e to the power j omega naught t e to the power minus j omega naught t. And now from the frequency shift property, we know e to the power j beta t x of t will have a Fourier transform pair of x of j omega minus beta. So, as shown before, we know Fourier transform of 1 is twice pi delta omega, and the Fourier transform of half is half times twice pi delta omega is equal to pi delta omega. So from the property, x of j omega can be written as half will have a Fourier transform of pi delta omega, and since e to the power j omega t is multiplied with half j omega naught t, so this term becomes something like this. X of t in our case is half, and e to the power j omega naught t is j beta t. So if we correlate these two terms, we can easily say that the value of beta will be equal to omega naught, and consequently the shift in the frequency instead of beta will be omega minus omega naught. And for the next term, it is also quite similar. Half will have a Fourier transform of pi delta omega. Here there was positive omega naught. Since there is a negative omega naught, this will have a Fourier transform of omega plus omega naught. So this is the required Fourier transform of cosine of omega naught. Now moving on to the next problem. We are to determine the Fourier transform x of t times e to the power minus at u of t. Now, since x of t will have a Fourier transform of x of j omega, then from the property frequency differentiation, we can write minus jt x of t will have a Fourier transform of ddw of x of j omega. Now we know e to the power minus at u of t has a Fourier transform as shown before to be equal to a plus j omega inverse. So if we multiply the if we multiply this term with a negative of jt e to the power minus at u of t, the right hand side will become ddw of a plus j omega, dd omega of a plus j omega inverse. So simply we have applied the frequency differentiation property. We have multiplied the right hand side with minus jt and the left hand side with negative of jt, and the right hand side becomes the differential form. This can be differentiated to a plus j omega can be differentiated and written as 1 over a plus j omega squared sorry, and as per the chain rule of differentiation, we need to differentiate this expression as well. A can be differentiated with respect to d omega to be 0, plus this term when differentiated will become j. So this becomes negative of j a plus j omega whole squared. So in the right hand side we can cancel this j with the j, this negative j with this j, and t e to the power minus at u of t will have a Fourier transform pair that is equal to a plus j omega squared, a plus j omega raised to the power of negative of 2. So this is the given expression if you look closely, and hence we have derived the Fourier transform of the given expression x of t. Moving on to the next problem. So in this example we have to determine the Fourier transform x of t, which is equal to 1 plus t squared. So if x of t has a Fourier transform of x of j omega, then from the previous problem we have seen that e to the power minus a modulus of t will have a Fourier transform of twice a over a squared plus omega squared. And if a equals to 1, then this expression said to be x of t and this to be x of j omega, x of t, let's rename this to be y of t and this y of j omega. So y of t sorry, will be equal to e to the power minus t, and the Fourier transform pair will be 2 times 1 plus omega squared. Now again we refer to the property of duality, which states capital X of t will have a Fourier transform pair twice by small x of negative omega. So in this case, capital X of t, that is this term, 2 by 1 plus this is y of j omega. When compared to capital X of t, the omega is replaced with t, so this becomes 1 plus t squared f of t twice pi remains as it is, and x of negative omega, that is y of t here, is equal to e to the power minus modulus of t. So e to the power minus modulus of, instead of t, this is replaced by minus omega. So twice pi e to the power minus modulus of omega, modulus of negative of omega is equal to modulus of omega, as we have seen from as we know from the property of absolute values. This will become s of omega, and so 1 over 1 plus t squared will have a Fourier transform twice pi e to the power minus omega divided by 2. Sorry, this question will be to the power minus 1. So 1 plus t squared to the power minus 1 will have a Fourier transform equal to pi e to the power minus omega. This is the required Fourier transform. So for the next problem, we have to find the Fourier transform of x of t, which is equal to sine of pi t e to the power minus twice t u of t. Now x of t, sine of pi t can be expanded using the Euler's relation to be 1 over twice j e to the power j pi t minus e to the power minus j pi t times e to the power 2t u of t. So x of t is equal to 1 over twice j e to the power j pi t e to the power minus 2t u of t sorry, minus e to the power minus j pi t e to the power minus twice t u of t. Just multiplying this common term to both the expressions. Let us mark it to be as equation 1. Now, since, as I have shown before, e to the power minus at u of t has a Fourier transform of a plus j omega, so e to the power minus 2t u of t will have a Fourier transform 2 plus j omega. Now, from the frequency shift property, the frequency shift property, we can write e to the power j beta t times x of t will have a Fourier transform x of j omega minus beta, and now using this property we'll try and find out the Fourier transform of the expression 1 of the equation 1. So Fourier transform of equation 1, which is x of j omega, will be the constant term 1 over twice j remains as it is, and we consider this part of the expression to be our x of t, and if this part is x of t, so the Fourier transform will be 1 over here is negative 1 2 plus j, and instead of omega, since instead of omega there is e to the power minus j pi t multiplied to this expression, in the frequency domain the Fourier transform will be shifted to omega plus pi from this property, where beta is the value of pi. Similarly, for this expression, if we consider it to be x of t, this will have a Fourier transform 2 plus j, this will be negative of pi, 2 plus j omega, but instead of omega, since this term is multiplied in the right hand side, in the left hand side, like this term of the property, so in the frequency domain the result will be shifted and becomes plus pi. Now you can leave the result up to this point, but I will try to simplify it a bit further. 1 over twice j plus j omega j pi plus 2j omega plus pi 2j omega minus pi plus j squared omega squared minus pi squared. This in turn can be written as 1 by twice j. This j omega cancels out. The 2 and 2 also cancels out. We are left with 2j times pi. Sorry, we are left with 2 2j times pi over 4 plus twice j omega twice j pi twice j omega twice j pi plus negative of omega squared plus pi squared. This 2j cancels. 2j pi will cancel with the negative 2j pi, and x of j omega becomes pi over 4 plus 4j omega minus omega squared plus pi squared, which is the required Fourier transform of the expression given in the questions. I hope the problem is clear to you all, and with that we move on to the last problem of our today's lecture. In the final problem, of today's lecture, we are required to find three terms. The first one is negative infinity to infinity x of j omega d omega. The second term being negative infinity to infinity x of j omega e to the power twice j omega d omega. And for the third expression, we have to solve for negative infinity to infinity x of j omega squared d omega. Now, also part of the question, what does x of t looks like? X of t looks like something like this, where this value is 1 and this part here is negative 1, this is negative 1, 0, this is 1, this is 2, this is 3. This is the time axis x of t. So now, from the synthesis and analysis equation, we can write from the direct transform x of j omega to be equal to negative infinity to infinity x of t e to the power minus j omega t dt, which is our analysis equation. And the synthesis equation x of t 1 over twice pi minus infinity to infinity x of j omega e to the power j omega t dt. Now, in order to solve the first expression of the given problem, what do you think we should take as our base equation for the analysis? What I mean to say is that should we follow the analysis equation or the synthesis equation in order to solve the first part of the problem? I hope it is quite clear that since this term shows quite a bit similarity with the synthesis equation, we shall have to move forward with the synthesis equation. So if you look closely for the first part of the problem, here we have got x of j omega. Instead of I'm sorry, there seems to be a problem. This will be d omega. This term is obsolete in the question and d omega remains as it is. So if we can just say if we can make this term to be equal to 1, we get the right hand side almost equal to the question that is provided here. So to do that, say we write x of 0 to be equal to 1 over twice pi minus infinity to infinity x of j omega e to the power j omega. Since t we have taken to be 0, this becomes 0 d omega. I hope that is clear. Now moving forward, minus infinity to infinity, I am writing the right hand side first. X of j omega remains as it is. E to the power j omega 0 is essentially equal to e to the power 0 and is equal to 1 times d omega. Since there was a 2 pi divided in the right hand side, this will be multiplied in the left hand side. So this becomes twice pi x of 0. So minus infinity to infinity x of j omega is equal, d omega is equal to twice pi x of 0. If we refer to the graph, x of 0, x at the point 0, the value is 1. So this becomes 1. So the result is twice pi. So we have solved the first part of the problem. Now moving on to the next part. Here given x of j omega e to the power 2j omega d omega. If you are familiar with the first part of the problem, this part is also very easy and needs a very little calculation compared to that of the first part, because we have established that by changing the value of the time axis variable, that is t, we can derive this expression, and in order to do so we shall have to do the same for this expression as well. So in the previous part we got the result by taking x of 0 to be equal to x of 0 and solving for that. But in this case the value we need to take is x of 2, because if x becomes t becomes 2, this term becomes j omega times 2 or 2j omega. So this expression suffices. So x of 2 is negative infinity to infinity. X of j omega will remain as it is, since it is not dependent on the time variable, e to the power 2j omega d omega. There is 1 over 2 pi over here, and in the right hand side, so we can write minus infinity to infinity x of j omega e to the power 2j omega d omega is equal to twice pi x of 2, and at the value